Program memory in the form of Ferroelectric RAM, NOR flash or OTP ROM is also often included on chip, as well as a typically small amount of RAM. Microcontrollers are designed for embedded applications. In contrast to the microprocessors used in personal computers or other general-purpose applications, microcontrollers are used in automatically controlled products and devices, such as automobile engine control systems, implantable medical devices, remote controls, office machines, appliances, power tools, toys and other embedded systems. By reducing the size and cost compared to a design that uses a separate microprocessor, memory, and input-output devices, microcontrollers make it economical to digitally control even more devices and processors. Mixed-signal microcontrollers are common, integrating analog components needed to control non-digital electronic systems. Some microcontrollers may use 4-bit words and operate at clock rate frequencies as low as 4 kHz. For low power consumption, they will generally have the ability to retain functionality while waiting for an event such as a button press or other interrupt power consumption, while sleeping maybe just nanowatts, making many of them well suited for long-lasting battery applications. Other microcontrollers may serve performance-critical roles, where they may need to act more like a digital signal processor, with higher clock speeds and power consumption. History. The first microprocessor was the 4-bit Intel 4004 released in 1971, with the Intel 8008 and other more capable microprocessors becoming available over the next several years. However, both processes required external chips to implement a working system, raising total system cost, and making it impossible to economically computerize appliances. The Smithsonian Institution credits T engineers Gary Boone and Michael Cochran with the successful creation of the first microcontroller in 1971. The result of their work was the TMS-1000, which became commercially available in 1974. It combined read-only memory, read-write memory, processor and clock on one chip and was targeted at embedded systems. Partly in response to the existence of the single-chip TMS-1000, Intel developed a computer system on a chip optimized for control applications. The Intel 8048, with commercial parts first shipping in 1977. It combined RAM and ROM on the same chip. This chip would find its way into over 1 billion PC keyboards, and other numerous applications. At that time Intel's president, Luke J. Valenter, stated that the microcontroller was one of the most successful in the company's history, and expanded the division's budget over 25%. Most microcontrollers at this time had two variants. One had an erasable EPROM program memory, with a transparent quartz window in the lid of the package to allow it to be erased by exposure to ultraviolet light. The other was a PROM variant which was only programmable once. Sometimes this was signified with the designation OTP, standing for one-time programmable. The PROM was actually exactly the same type of memory as the EPROM, but because there was no way to expose it to ultraviolet light, it could not be erased. The erasable versions required ceramic packages with quartz windows, making them significantly more expensive than the OTP versions, which could be made in lower-cost opaque plastic packages. For the erasable variants, quartz was required, instead of less expensive glass. For its transparency to ultraviolet, glass is largely opaque to UV, but the main cost differentiator was the ceramic package itself. In 1993, the introduction of EEPROM memory allowed microcontrollers to be electrically erased quickly without an expensive package as required for EPROM, allowing both rapid prototyping and in-system programming. The same year, Atmel introduced the first microcontroller using flash memory, a special type of EEPROM. Other companies rapidly followed suit, with both memory types. Cost has plummeted over time, with the cheapest 8-bit microcontrollers being available for under 25 United States cents in quantity in 2009, and some 32-bit microcontrollers around $1 for similar quantities. Nowadays, microcontrollers are cheap and readily available for hobbyists, with large online communities around certain processors. In the future, MRAM could potentially be used in microcontrollers as it has infinite endurance and its incremental semiconductor wafer process cost is relatively low. Volumes in 2002, about 55% of all CPUs sold in the world were 8-bit microcontrollers and microprocessors. Over 2 billion 8-bit microcontrollers were sold in 1997, and according to Semico, over 4 billion 8-bit microcontrollers were sold in 2006. More recently, Semico has claimed the MCU market grew 36.5% in 2010 and 12% in 2011. A typical home in a developed country is likely to have only 4 general-purpose microprocessors but around 3 dozen microcontrollers. A typical mid-range automobile has as many as 30 or more microcontrollers. They can also be found in many electrical devices such as washing machines, microwave ovens, and telephones. Historically, the 8-bit segment has dominated the MCU market. 16-bit microcontrollers became the largest volume MCU category in 2011, overtaking 8-bit devices for the first time that year. IC Insights believes the makeup of the MCU market will undergo substantial changes in the next 5 years, with 32-bit devices steadily grabbing a greater share of sales and unit volumes. By 2017, 32-bit MCUs are expected to account for 55% of microcontroller sales. In terms of unit volumes, 32-bit MCUs are expected to account for 38% of microcontroller shipments in 2017, while 16-bit devices will represent 34% of the total, and 8-bit designs are forecast to be 28% of units sold that year. The 32-bit MCU market is expected to grow rapidly due to increasing demand for higher levels of precision in embedded processing systems and the growth in connectivity using the Internet. In the next few years, complex 32-bit MCUs are expected to account for over 25% of the processing power in vehicles. IC Insights, MCU market on migration path to 32-bit and ARM-based devices in 2012. Following a global crisis, a worst-ever annual sales decline and recovery in average sales price year-over-year, plunging 17%, the biggest reduction since the 1980s. The average price for a microcontroller was 88 cents. In 2012, worldwide sales of 8-bit microcontrollers were around $4 billion because they were so useful that many companies needed them to be able to progress into better technology. In 2012, 4-bit microcontrollers also see significant sales. In 2015, 8-bit microcontrollers can be bought for $0, 311, 16-bit for $0, 385, and 32-bit for $0, 378. Embedded design. A microcontroller can be considered a self-contained system with a processor, memory and peripherals, and can be used as an embedded system. The majority of microcontrollers in use today are embedded in other machinery, such as automobiles, telephones, appliances, and peripherals for computer systems. While some embedded systems are very sophisticated, many have minimal requirements for memory and program length, with no operating system, and low software complexity. Typical input and output devices include switches, relays, solenoids, LEDs, small or custom liquid crystal displays, radio frequency devices, and senses for data such as temperature, humidity, light level, etc. Embedded systems usually have no keyboard, screen, disks, printers, or other recognizable I/O devices of a personal computer, and may lack human interaction devices of any kind. Interrupts. Microcontrollers must provide real-time response to events in the embedded system they are controlling. When certain events occur, an interrupt system can signal the processor to suspend processing the current instruction sequence and to begin an interrupt service routine. The ISR will perform any processing required based on the source of the interrupt, before returning to the original instruction sequence. Possible interrupt sources are device-dependent, and often include events such as an internal timer overflow, completing an analog-to-digital conversion, a logic level change on an input such as from a button being pressed, and data received on a communication link, where power consumption is important as in battery-operated devices. Interrupts may also wake a microcontroller from a low-power sleep state where the processor is halted until required to do something by a peripheral event. Programs. Typically microcontroller programs must fit in the available on-chip program memory, since it would be costly to provide a system with external, expandable memory. Compilers and assemblers are used to convert high-level language in assembler language codes into a compact machine code for storage in the microcontroller's memory. Depending on the device, the program memory may be permanent, read-only memory that can only be programmed at the factory, or program memory that may be field-alterable flash or erasable read-only memory. Manufacturers have often produced special versions of their microcontrollers in order to help the hardware and software development of the target system. Originally these included EPROM versions that have a window on the top of the device through which program memory can be erased by ultraviolet light, ready for reprogramming after a programming and test cycle. Since 1998, EPROM versions are rare and have been replaced by EEPROM and Flash, which are easier to use and cheaper to manufacture. Other versions may be available where the ROM is accessed as an external device rather than as internal memory. However, these are becoming increasingly rare due to the widespread availability of cheap microcontroller programmers. The use of field programmable devices on a microcontroller may allow field update of the firmware or permit late factory revisions to products that have been assembled but not yet shipped. Programmable memory also reduces the lead time required for deployment of a new product, where hundreds of thousands of identical devices are required. Using parts programmed at the time of manufacture can be an economical option. These mask-programmed parts have the program laid down in the same way as the logic of the chip. At the same time, a customizable microcontroller incorporates a block of digital logic that can be personalized in order to provide additional processing capability. Peripherals and interfaces that are adapted to the requirements of the application. For example, the AT91 CAP from Atmel has a block of logic that can be customized during manufacture according to user requirements. Other microcontroller features. Microcontrollers usually contain from several to dozens of general-purpose input/output pins. GPIO pins are software configurable to either an input or an output state. When GPIO pins are configured to an input state, they are often used to read senses or external signals. Configured to the output state, GPIO pins can drive external devices such as LEDs or motors, often indirectly, through external power electronics. Many embedded systems need to read senses that produce analog signals. This is the purpose of the analog-to-digital converter. Since processors are built to interpret and process digital data, i.e., 1s and 0s, they are not able to do anything with the analog signals that may be sent to it by a device. So the analog to digital converter is used to convert the incoming data into a form that the processor can recognize. A less common feature on some microcontrollers is a digital to analog converter that allows the processor to output analog signals or voltage levels. In addition to the converters, many embedded microprocessors include a variety of timers as well. One of the most common types of timers is the programmable interval timer. A pin may either count down from some value to 0, or up to the capacity of the count register, overflowing to 0. Once it reaches 0, it sends an interrupt to the processor indicating that it has finished counting. This is useful for devices such as thermostats, which periodically test the temperature around them to see if they need to turn the air conditioner on, the heater on, etc. A dedicated pulse width modulation block makes it possible for the CPU to control power converters, resistive loads, motors, etc., without using lots of CPU resources in tight timer loops. Universal Asynchronous Receiver Transmitter block makes it possible to receive and transmit data over a serial line with very little load on the CPU. Dedicated on-chip hardware also often includes capabilities to communicate with other devices in digital formats such as inter-integrated circuit, serial peripheral interface, universal serial bus, and Ethernet. Higher integration. Microcontrollers may not implement an external address or data bus as they integrate RAM and non-volatile memory on the same chip as the CPU. Using fewer pins, the chip can be placed in a much smaller, cheaper package. Integrating the memory and other peripherals on a single chip and testing them as a unit increases the cost of that chip, but often results in decreased net cost of the embedded system as a whole, even if the cost of a CPU that has integrated peripherals is slightly more than the cost of a CPU and external peripherals. Having fewer chips typically allows a smaller and cheaper circuit board, and reduces the labor required to assemble and test the circuit board, in addition to tending to decrease the defect rate for the finished assembly. A microcontroller is a single integrated circuit, commonly with the following features. Central processing unit, ranging from small and simple 4-bit processors to complex 32-bit or 64-bit processors. Volatile memory for data storage. ROM, EPROM, EEPROM or flash memory for program and operating parameter storage. Discrete input and output bits, allowing control or detection of the logic state of an individual package pin. Serial input, output such as serial ports. Other serial communications interfaces like I2C, serial peripheral interface and controller area network for system interconnect. Peripherals such as timers, event counters, PWM generators, and watchdog. Clock generator, often an oscillator for a quartz timing crystal, resonator or RC circuit. Many include analog to digital converters, some include digital to analog converters. In-circuit programming and in-circuit debugging support. This integration drastically reduces the number of chips and the amount of wiring and circuit board space that would be needed to produce equivalent systems using separate chips. Furthermore, on low pin count devices in particular, each pin may interface to several internal peripherals, with the pin function selected by software. This allows a part to be used in a wider variety of applications than if pins had dedicated functions. Microcontrollers have proved to be highly popular in embedded systems since their introduction in the 1970s. Some microcontrollers use a Harvard architecture, separate memory buses for instructions and data, allowing accesses to take place concurrently. Where a Harvard architecture is used, instruction words for the processor may be a different bit size than the length of internal memory and registers, for example, 12-bit instructions used with 8-bit data registers. The decision of which peripheral to integrate is often difficult. The microcontroller vendors often trade operating frequencies and system design flexibility against time-to-market requirements from their customers, and overall lower system cost. Manufacturers have to balance the need to minimize the chip size against additional functionality. Microcontroller architectures vary widely. Some designs include general-purpose microprocessor cores, with one or more ROM, RAM, or I/O functions integrated onto the package. Other designs are purpose-built for control applications. A microcontroller instruction set usually has many instructions intended for bit manipulation to make control programs more compact. For example, a general-purpose processor might require several instructions to test a bit in a register and branch if the bit is set, where a microcontroller could have a single instruction to provide that commonly required function. Microcontrollers typically do not have a math coprocessor, so floating-point arithmetic is performed by software programming environments. Microcontrollers were originally programmed only in assembly language, but various high-level programming languages are now also in common use to target microcontrollers. These languages are either designed specially for the purpose, or versions of general-purpose languages such as the C programming language. Compilers for general-purpose languages will typically have some restrictions as well as enhancements to better support the unique characteristics of microcontrollers. Some microcontrollers have environments to aid developing certain types of applications. Microcontroller vendors often make tools freely available to make it easier to adopt their hardware. Many microcontrollers are so quirky that they effectively require their own non-standard dialects of C, such as SDCC for the 8051, which prevent using standard tools even for code unrelated to hardware features. Interpreters are often used to hide such low-level quirks. Interpreter firmware is also available for some microcontrollers. For example, BASIC on the early microcontrollers Intel 8052, BASIC and 4th on the Zilog Z8 as well as some modern devices. Typically these interpreters support interactive programming. Simulators are available for some microcontrollers. These allow a developer to analyze what the behavior of the microcontroller and the program should be if they were using the actual part. A simulator will show the internal processor state and also that of the outputs, as well as allowing input signals to be generated. While on the one hand most simulators will be limited from being unable to simulate much other hardware in a system, they can exercise conditions that may otherwise be hard to reproduce at will in the physical implementation, and can be the quickest way to debug and analyze problems. Recent microcontrollers are often integrated with on-chip debug circuitry that, when accessed by an in-circuit emulator via JTAG, allow debugging of the firmware with a debugger.